Okay, let's start lecture 9. Last time we did lecture 8 part 2 where we talked about the Jacobians and Jacobi matrix and so forth. And at the end of that lecture I said next time we will talk about the applications of differentiations and so forth. Yes, but the most interesting and probably something you are not really thinking or you really don't know it is an application of differentiation is actually integration. So this time I will talk about the integration and I'll tell you how integration becomes an application of differentiation. Okay. Okay. So we'll start from robot again. A robot. Of course, you do have lots of motors, and the motor generates torque. We have done this several times already. And then what? We have done this again. We have done this already, so let's do it again. Generates angular acceleration. That's Newton's law. F equal ma. Torque tau is equal to I times omega dot, theta double dot. So that's something we already know. So from this equation, theta double dot is equal to 1 over I times torque. So if you know the torque, then you should be able to find, just an acceleration? Well, you should be able to find what the angle is because if you apply the torque, then it moves. So as a result, the angle changes. So we should be able to compute how much angle change occurred. Okay. How can we find the angle? That's called the integration. The integration. So that is a mathematical tool we use to find an angle from the torque. Okay, so it looks like this one here. From angular acceleration, you perform integration, you get angular speed, and then you perform integration again, you get angle. So this is the process I'm going to show you today. Okay. Okay, differentiation. Let's take a look at differentiation. Differentiation was from position to rate of change in position. All right? And as I showed you, the integration goes the other way around, right? Rate of change to total variation. That's what integration is. Really? Well, that's exactly what I said. In other words, from speed to position is what integration can do for us. That's handy. That's the reason why we can use this integration as a tool to find the angles. Really, really. Question here. History. Well, if you look at the history of integration in mathematics, the history was invented for area computation. Why? In old days, in the Greek days, okay, the tax was proportional to the amount of land you own. If you own a large land, you have to pay more tax. If you own a small land, you pay small tax. So, the computing the land area was a very important job for the government. Okay? So integration was actually developed for that particular purpose. So let's take a look at that integration of area computation. Okay? And after that, I will show you how to answer this really question. Okay. First example. Constant function, like this one here. Well, if you, for the area, we are looking at this one here. how can you compute this area? Well, since this is a rectangle, we all know how to compute the area, right? Height times the length here. So that's area of rectangle is equal to height times width, which is equal to, for this particular case, that's 6 and 3, that's 18. No question about that. Nothing difficult at all. Okay, how about this one here? Wow, how can you compute the area here? It's not that easy, right? Changing function. Okay, so how do you approach for that problem? Well, engineers, second fish under willow tree, remember that? The second fish under willow tree, meaning that if you can use a tool, then try to use that tool again. The tool here we are talking about is rectangle. We know how to compute the area of the rectangle. So, therefore, divide and conquer, n columns here, n of them. Each one of them is a rectangle. So each one of them we can compute the area. And, well, as you can see, the total sum of those areas must be very close to whatever the original area we wanted to compute. So, first example here. And here we have some numbers here, not numbers, but the notations here. Well, this function is called omega t, and at ti, of course, that's the value is omega ti. So, the height, omega ti, and this delta t, you divided t, f, t, 0 interval into n of them. So, putting all of them together, delta omega yi times delta t, where delta t is tf minus t0 divided by n. So that's one column, one rectangle. So the total area is this, t0 plus t1 plus blah blah blah, tn minus 1. The last one is this one here. Okay, so you add all of them together. For that, we do have a very nice, handy notation here, right? Large sigma. I is equal to 0 to n minus 1, omega ti times delta t, meaning I changes from 0 to n minus 1 and add them together. That's what that is. All right. So let's actually compute this one here. Okay. But actually compute, well, I'll do the actual computation in a minute, okay? Using omega ti, something which we know. All right. If you look at this one here, how can we make the approximation, or should I say that the sum of those, all of those columns close to the original area? Of course, those are all of those are errors, right? How can you minimize the amount of those errors? Of course, if you make delta t smaller and smaller, that becomes smaller and smaller. So the error between the sum of those columns and the original area becomes smaller and smaller. You agree? Please agree with that. Naturally, that intuition tells you that. So what we want to do is take the limit of delta t goes to 0. Wow, another limit operation. We have done limit operation in differentiation, and in integration we do the same thing. Okay, so here, so integrations and differentiations are close to each other? Yes, but I'll tell you that in a minute. So before that, let's look at this one here. So delta t goes to 0, meaning that you have more columns, meaning that n goes to infinity, right? Number of columns becomes infinity. So for this summation is done in terms of n, so that's limit n goes to infinity of this one here. So that's what we do. We do? Yeah, we do later. So the notation here, instead of writing all of these again and again, limit blah, 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 what we do is this here. And this one has a name, Riemann Integral. Famous mathematician Riemann had come up with this integration. That's why this one is called the Riemann Integral. Okay. Incidentally, before the Riemann Integral, without limit, this one is called the Riemann sum, because you are summing up lots of different terms. And when you take the limit, then becomes integral. So sum becomes integral when you're taking the limit. All right. After all, this is the integration you know. Okay. That's the important part. You have learned integration probably in high school. And actually, the integration you have learned is Riemann integral. So there is a name for it. Well, why, you ask? Right? The reason is very simple, that there are other integrations in the world. Mathematicians have invented many different types of integration. And that's why we have to give the names for it. Riemann integral, and there are many others. But this one here is the one which is simplest, should I say? So we learn in high school. All right. So now, examples. Well, let's start from a simple one. Omega t is equal to 2t. And from 0 to 3, integration. All right. So if you look at delta t, 3 minus 0, tf minus t0 divided by n, so 3 over n. Okay. And then, come on. Ti, the positions, is t0 plus I times delta t. And t0 was 0. Okay. So therefore, I times delta t is this one here, so 3I over n. Okay. So therefore, omega at ti is equal to twice as much of ti, this one here, so ti, so that's 6I over n. Okay. So this summation of omega ti times delta t becomes summation of 6I over n multiply n divided by, 3 divided by n. That's, and this. All right? So, n, 3, 6, all of those have nothing to do with the summation. So let's get them out of the summation. Here you have a summation of I. Summation of I, that's a very famous one, right? 1 plus 2 plus 3 plus and n minus 1 up to n minus 1. And I assume that you already know the answer for that. And if not, I will show you that and other summations later, not today. But anyway, this one here is 1/2 of n minus 1. This is the largest one, plus 1. So if you compute this one here, that's n squared, 9, and this. That's Riemann sum. That's Riemann sum. Okay? To get the Riemann integral, you need to take the limit. So s is equal to limit n goes to infinity of this one here, but n, there are lots of cancellations. You only got 1 minus 1 over n. And n goes to infinity, 1 over n, of course, goes down to 0. So the answer is 9. All right, so let's take a look at this area. 3, 6. This is right triangle. So therefore, right triangle, once again, let me just get rid of this. Okay. So this is the right triangle. Area is equal to the width and height divided by 2. That's 9. So those two were equal to each other. Okay, 9 and 9. No problem. Well, let's take a look at this one here. I said area. But if you take a look at this goes down to the negative side. Area, when you look at the area, it has to be positive, right? However, integration is more general. So let's take a look at this function, minus 2t from t is equal to 0 to 3. Okay? Joint can move backwards too. That's the reason why. Joint can move this way or that way, either way, right? Okay? So the speed could be negative or positive or whatever. Okay? So we should be able to compute they do the integration of negative side as well. And if you compute delta t, there's no problem, and ti, no problem, omega ti. The only difference is this minus sign here. So therefore, you have minus sign here. That's the only difference. Exactly the same thing as you have done, so minus thing. That's the only difference. So if you take the limit, then minus 9. Well, let's take a look at this one here. Right triangle, but width is equal to 3, but the height is minus 6. Instead of 6, minus 6. So if you multiply this one here, you get minus 9. Once again, exactly the same thing. So therefore, from this one here, original area, the idea of area was greater than 0, but integration can be less than 0 again. So integration can have directions, this way or that way. All right. Okay, so how about this one here? Part of it is on the plus side, the other part is on the negative side. So what's going to happen? Okay, so the function is 1 minus t from t equals 0 to 3. Joint can move both ways. Move this way and go back, like kicking. When you do the kicking, first you take your leg backwards and then kick, right? So can move both ways, so therefore plus minus both of them. All right, this one here. But the equation is pretty much the same, except omega ti is not going to be different because that's 1 minus t. So 1 minus 3i over n. That's the only difference we have. So break down into two parts. We get 3 over n summation and this one here. This part is, once again, excuse me, we already computed this part. So this one here, 3 over n coming out, then the only thing left is 1. So you are adding 1 from 0 to n minus 1, so n minus 1, 1. So that's, 1 from I is equal to 0, so n go. Now there are n of them. All right, so that's 3 minus this entire thing, and this one here, and blah, 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 and if you take the limit, and 3 minus 1/2 of 9, that is going to be minus 2/3. So what this number represents? What do you think is that? Well, if you look at this one here, this part is on the positive side, this part is on the negative side. So the area, this one here is positive, area, this one here is negative. So let's add those two areas considering the positivity and negativity. Then that's 1. Well, let me call this 1 and 2. Area 1 is 1 times 1 divided by 2, so 1/2. Area 2 is 2 and minus 2 divided by 2, that's minus 2. So the total area is 1/2 plus minus 2, that's negative 2/3. So, integration can go above or below 0 freely. Regardless of which way it goes, you can compute. Great. So now we know that integral can go, the area can have negativity and positivity. And we can go ahead and do the lots of computations using limits and so forth. Okay. So before going into that more solid examples and so forth, I'd like to just comment on this notation here. Well, we have changed this limit summation to this sign here. So this here, the summation sign, if you look at this one here, it has been changed to this, and where star means that's a placeholder. So you put something there, all right? Okay, so next, I is equal to 0, the lower limit becomes t0 here. And then the other side, n is equal to 1, n minus 1, which is the upper limit, which is changed to tf, the final time. And omega of ti is changed to omega t, namely ti is changed to t. Okay, because as n gets larger and larger, and I just becomes so many of them, so it just becomes t. All right. And delta t we write as dt instead of delta t. Delta t is something which you can measure, the small thing. And dt is something you cannot measure. It's a real small thing. Okay. So if you do this conversion, you get this notation here. That's the one I'm sure you got used to for the integration. Okay. So the integration is this set, integral of this and something coming into here and dt. And whatever coming into here is called the integrand. We will show the different examples with different integrals later. Well, one thing I'd like to talk about is this dummy variable for integration. Well, this is dummy variable for integration. What does it mean? All right. But this dummy variable happens to be very, very important in the sense that it is not the regular variable. So more in coffee break, next one. All right. Model of dummy variable. What's wrong with this one here? Well, I don't think you think this is wrong, right? This is something which you have learned in high school, I'm sure. If you're not, you're good. But most of the time, you learn like this one here. F of t is equal to integral from 0 to t of t dt. What's wrong with it? Of course, there is something wrong with this one here. By the way, as I said in the former slide, this is called integrand. All right. Fact. Two of them, actually. First one, t in ft here is called the current time or current position or whatever. If that was x, that's current position. But I'm using t, so that's time, so it's current time. Whereas t in ft here in integrand, this is just a dummy variable for integration, like the slide I gave you the before. All right. So the fact is a dummy variable moves from the lower limit to the upper limit from 0 to t. Right? So dummy variable cannot be the same as the current time t. So this variable, whatever this one here, needs to move from here to there. But it's t. So say, for example, if you have f of 2, that's 0 to 2 integral of f of 2. No way, right? So what you need to do is must use different variable for dummy variable. Like this one here, I use u for the dummy variable. Okay, it is very important in the sense that you will have something when you learn control theory for the robots, how to control. Okay, you will come up with something more than this one here. You will come up with something like f of t minus u. Aha, here. This one is the current time, and this one here is the time variable. So you must make distinction between these two. Okay, so that's the end of this lecture here, and next time I'll go into the integral, but which does not represent the area. Thank you.